Hello, class. This is an additional lecture, a continuation of the logic material. So for whoever wants to listen, I made some extra slides on the few of the last subsections of chapter 1 that are on our reading list. And this is also part of the first homework. So that's why I thought you would especially either all or some of you might want to listen to this extra lecture. Okay, so let's jump into it, to where we have left off last time. So, okay, here's the slide that was the last one we had, it's we introduce one more logical operation, bi-conditional. A bi-conditional is expressed with this double arrow in both directions, and it's read if and only if. So this statement is read if P, if and only if Q. So that, to say this is equivalent to saying the following, namely, by saying P and if and only if Q, we mean a conjunction of two things. First of all, P implies Q, and secondly, Q implies P. This side says that if P, then Q, and this one says if Q, then P. One of them can be read as P only if Q. Okay, so this one is P if Q, right? P holds if Q holds. And this one can be read P only if Q. This is kind of a funny way to read it, but it is true. So what does it mean that P only if Q? It means that without Q, P couldn't happen. P only if Q. In other words, Q is a necessary consequence of P. And that's indeed what this implication says, right? So you cannot have a world in which P is true, but Q is false. All right. So P, if and only if Q, is true if basically P and Q have the same value. So it's true either if both are false, which is this row, or if both are true. And why is that? Because it's a conjunction. So both this part and this part must hold. This part, P implies Q, holds everywhere in all four rows except this one. This one is the row that violates P implies Q, right? Because in this row we have P holds, but Q somehow doesn't. Q is supposed to, this statement says that Q is implied by P. So this violates this part of this implication, right? This row violates this implication, right? Because if we say that Q implies P, then it cannot be that Q is true and P is false. Therefore, this is violated because this part is violated. And since this is equivalent to the conjunction of the two, the resulting truth table is this. Okay. So by now, basically, we have seen a bunch of logical equivalences between the laws that are always true, right? So we have seen the associative laws that are simple, that you can rewrite, that the order of conjunctions does not matter. And indeed, whenever you see such a thing, you could rewrite it ignoring the brackets. So both of these could be rewritten as P and Q and 4 without brackets. Likewise, disjunction is associative, meaning that you can perform it in any order, right? So this junction of P or Q and then disjuncted by R is the same as P disjuncted by disjunction of Q and R. So we have seen that conditional can be expressed as disjunction. So P implies Q can be expressed in this way. right? Either not P or Q. We have seen De Morgan's laws, right? That a negation of a conjunction is the same as disjunctions of negations, or negation of disjunction of the disjunction is a conjunction of negations, right? And counterpositive, right? That P implies Q can be restated as not Q implies not P, right? We dwelt on each of them, and this is just putting them all together. In fact, in the book, you have more of these, right? So here is, some of them are sort of, all of them are in a sense obvious. Okay, what does it mean, obvious? This means that you stare at them and you make sure that you understand them. And once you do, then you should be like, oh, yeah, okay. And sort of at that point, you don't need to remember the names, right? So let's look. For example, P or P is the same as to say P, right? And likewise, if somebody says P and P, it's the same. It's just this person is just saying P, that's all. Associative laws we've seen, commutative laws, immediate, right? That the order of elements when you say or does not matter. And likewise, if you say and, it does not matter. Now, okay, let's skip this one, identity law. So that's a very simple one. If I say either false or something, that's equivalent to that something. Likewise, if I say it's true, the following is true, a true thing and P. Well, I shouldn't, there was no point saying the following is true, the true thing and P, right? I could just have said P. These two are equivalent. Likewise, on the other hand, if I say that the following is the case, a false thing and a P, well, that's always false. It does not matter what P is. This will always evaluate to false. Likewise, if I say either of the two things holds, something true and some statement P, well, that's true, no matter what P statement is, right? Double negation. If I say not P, that's the same as to say P. And you can see the truth table for that, right? Like a negation is a flip. So if you flip things twice, you're getting back to the same thing. And so these laws are kind of immediate. If somebody says, it's both the case that something holds and that that same thing does not, well, that person said a false statement, right? That statement could not be true. Does not matter what that thing is, because either case of P being true, then this part is false, so therefore conjunction is false. If P is false, then this conjunction is false immediately, right? Likewise, in this junction, if I say it's either true that something holds or that it doesn't, well, I didn't say much. It's a true thing. Does not matter what that something is, right? De Morgan's laws. Here, these are not, so this we have seen, these two, distributive and absorptions, are not obvious. You kind of have to stir them a little bit and sort of read them slowly and then see, aha, yes, okay. So let's not go through them. Obviously, you can verify them on your own. You are not responsible for remembering their names, except De Morgan, okay? And except that you should be familiar basically with all of them. You should be able to state them. You are not responsible to remember absorption and distributive laws, okay? It's nice if you do, but you don't have to remember them. You can rewrite them. All the others are should be part of your bloodstream. So let's look at the distributive laws, because they're a little bit tricky. Let's see. So are these laws obvious? So this is an extra stuff not in the book. I just wanted to compare logical operations and arithmetics. So look, associative laws, okay, well, this is kind of obvious. Like, for example, laws in arithmetics, plus and multiply are associative. And we know this since first grade of elementary school, and you don't need to remember what it's called. You basically know this is always true. Likewise, that addition and multiplication is commutative, that you can switch this order and it does not matter. But look at the distributive laws. So let's say that the conjunction is kind of like a multiplication. In fact, mod 2, it is a multiplication, right? If P and Q are 0 and 1, if you think of true or false instead of as a 0 and 1, then actually conjunction is a product, right? If P is 0 or Q is 0, the product is 0. The only case a product is 1, like conjunction, is if P and Q are both 1. All right. So if we think of conjunction as a product, and let's think of disjunction as perhaps an addition. So, well, you do have a distributive law like this in over arithmetics. It's true. But this distributive law is not a law, it's a false. I mean, maybe there is some ABC which satisfy it, but it's definitely not true for all ABC. And in that sense, it's not a law, right? It doesn't hold overall integers. So why is that? And this is true? Well, you can think of this, that basically the conjunction is like a product, but disjunction is not a sum. The case which violates this being a sum is this case. If P and Q are both true, then addition is true. And if you do arithmetics mod 2, right, which is just modulo 2, so the only thing that matters is whether a number is even or odd. If it's odd, then it's a 1, and if it's even, then it's a 0, right? So 2 becomes 0, so this is not true. This is not a disjunction, because disjunction is 1 whenever any of these guys are 1, and 0 only if both are 0. Well, XOR, it's an addition. So XOR, the exclusive OR, which is denoted this way, corresponds to an arithmetic addition. So how come this law holds, distributive law holds over, in Boolean logic, but the sort of corresponding quote unquote law in arithmetic does not? Well, because addition is not a disjunction. Okay. If you do want, so this is all I said already, and if you do want to render the inclusive or the standard one, the inclusive one, as an arithmetic operation, you could do it this way. So it's an XOR P plus Q plus an AND, right? An AND is a 1. For most cases, an AND does not matter, right? Whenever P and Q is 0, then adding this does not matter. It only matters when P and Q are both 1, and then it's going to correct, right? Because in this case is 1, 1, 1, so it's 3 mod 2, that's 1. And once you do this arithmetic formula and stick it in there for disjunction and here, then the arithmetic rendering will be true. All right, back to the usual programming. So let's introduce the concept of a predicate. A predicate is basically a function. It's a function where over some variables. So let's define p of x, okay, some function of x, as a preposition that x is prime. Now, for any particular value of x, this is a preposition. But if x is not instantiated, then it is not a proposition. It is a predicate. It's a function. Just like, when I say f of x, and I don't say what x is, that's a function. But for every x, f of x is a particular value, right? So in the case of propositional logic, the value is truth or false. So for example, take x equals 5. So if I instantiate this proposition with value x equals 5, my proposition becomes p of 5. My predicate, sorry, if I instantiate this predicate with x equals 5, then I get a proposition. The proposition is p of 5. What is that proposition? Well, it's equal to 5 is prime. It's a statement. It's a proposition. And it happens to be true. For x equals 6, the proposition p of 6, an instantiation of this predicate for x equals 6, is the following proposition. 6 is a prime number. It's a proposition. It's either true or false, and it's false, right? 6 is not a prime. 6 is a product of 2 and 3. So predicates can be thought of functions whose values are propositions. A variable in a predicate must have, there is an associate concept in a predicate. When I say p of x is a predicate, I have to specify what domain it goes over. Just like in a function, I have to specify the domain. Otherwise, the function might not be well defined. Excuse me. Sorry about that. Okay, so it is a set of possible arguments, possible values for x. So in other words, an argument of this function. Sometimes the domain can be implicit. For example, when I say that my predicate is of p of x is that x is prime, a sort of implicit domain are first of all integers. It makes no sense to talk about a non-integer number as prime or not prime. And so negative numbers, nobody would say that. And also as 0, right? So there is an implicit domain or positive integers. In this class, we will not count on identification of in the implicit domain, okay? Because we want to be precise. But in real life, people say things like a predicate, and they assume that you understand what the domain is. So let's look at some examples. So let's say that the domain is a set of students in a class from the 26, conveniently as many as letters. Ahmed, Beatrice, Carlos, Zach. Okay, so and a predicate T of x is that student X got an A in the class. So when I say T of Beatrice, I'm basically saying that Beatrice got an A, because if you instantiate the statement with x equal Beatrice, that's the statement you got. The statement Beatrice got an A is a proposition. It might be true, it might be not. Right? I don't know Beatrice. Maybe she got an A, maybe not. If I can also have a compound expressions involving predicates, right? So T of Carlos and T of Zach. These are two different propositions, and I conjunct them. In other words, I say both this is true and this is true, and this basically means Carlos got an A, and also Zach got an A, right? So I could just express it concisely as Carlos and Zach both got an A. Or perhaps an implication that if Zach got an A, then so did Beatrice. Again, these compound propositions are also propositions, right? So in some, perhaps, it so happens that Zach got an A and Beatrice didn't, in which case this implication is false. So predicates could come with, could make state propositions, not by instantiating the variable inside, but by preceding the whole the predicate with a quantifier. And there's two quantifiers, existential and universal. Here's the existential one. If this statement is read as there exists x such that predicate t instantiated with x is true. In other words, t of x holds. Okay. And by holds, I don't mean true. Okay. So this statement is true if it is the case that there exists an x which makes the x true. In other words, if tx is true for at least one value of x in the domain, right? So it exists, perhaps many, perhaps one, at least one. That's what the statement says. In common English, if I say, if the statement is true about every integer, and I say, there exists a positive integer that is greater than 0. You're like, huh? Well, because it's true for every integer, but it's also true for some, right? It's true for one, it's true for all. I don't care. It's true for one, and therefore this exists, makes sense, right? And it's false if the predicate is false for every value of x in the domain. So for example, let's look at the positive integer domain. So 1, 2, 3, right? And let's look at the statement. There exists an x such that its square is equal to itself. Well, most of the time it's not true, but it is true for one. One satisfies this, right? And if I define this domain as integers, not just positive integers, then there will be a second example, a 0. It's also true for 0. So it's true for 2, but I don't care. As long as it's true for 1, it's true. Let's look at this one. There exists an x such that 2x is x. Well, over this domain, it is false, right? Because this statement implies subtract x from both sides, that x is 0. And x equals 0 is not part of this domain. All right? So it's actually false over this domain. So it very much matters what the domain is. This statement would be true for all integers, or even for all non-negative integers, right? Because of 0 is true for 0, and 0 does belong to these sets. But it becomes false when the domain is changed to just positive integers. All right. So the domain makes these quantifiers, quantified statements could change the truth value of the quantified statement. Here is a universal quantifier. It is read as for all x. It holds that t of x. Okay. So we read it differently, not just this part, okay, because we say for all instead of there exists, but also we don't say such that. It wouldn't, English wouldn't render this correctly, right? So we say for all x, it holds that t of x. So the statement is true if for every value of x in the domain, t of x holds, false otherwise. So you need, if you want to check whether, if you want to argue that this statement is false, all you need to do is to find a single x which makes t of x not hold, right? Likewise, this is sort of counter-positive is true. If you want to prove that this is true, you only need one example. On the other hand, if you want to argue that it is false, then you have to argue that t is false for all, which is always kind of harder, right? And this is a flip. If you want to argue that this is false, then you need a single one on which t of x does not hold. But if you want to argue that this is true, then you need to argue that t of x is true for all x, right? Let's look at some examples. So let's say a statement is same domain, positive integers. For all x, it holds that x squared is x itself, right? That's obviously not true. Just pick any number, let's say 2, and it violates it, and that's it. You don't need to look at any other cases of x. Let's say for all x squared is at least x. Well, this is actually true, right? So how do you argue it exactly? Well, you can argue it by arithmetics. It's not really hard. That this function is larger than x for all In fact, this is true for all integers, not just positive integers, right? What about this statement? That x squared is always greater than x. You need only one counterexample, and indeed, over this domain, there is only one counterexample, and it's this one, x equal 1. 1 squared, which is 1, is not greater than 1, right? That's the only counterexample, but that's all you need. In case of if you look at the existential quantifier of a finite domain, then to say that there exists an x such that tx, which can be expressed as, there's many ways to say it here for the statement x got an A. There is a student who got an A, some student got an A, at least one student, and perhaps some students got an A, right? And here we get to ambiguities of English, right? Because if a professor says that, you can be like, well, he implies that there is more than one, right? Well, we're going to interpret this as there is no such implication, right? But obviously in human speech, there is one. So if you look at this for finite domains, then you can express this quantified statement as one big disjunction. So when a domain is finite, and I say there is some x that satisfies this predicate, well, I can say it in this manic but equivalent way. The predicate holds for either the first guy or the second or the third to the last. It's just a disjunction of individual statements about these people. Notice it's true in the same set. So this thing is true if there is one guy which makes t of x is true, and so is this one. You just need one of them to be true for the whole disjunction to hold. Likewise, universal quantifier on a finite domain can be restated as a one big conjunction. To say that something is true for all x is to say that it's true for the first, and true for the second, and true for the third, and true for all of them, right? It's just that if the domain is infinite, like integers or rationals or whatever, right? I cannot say this statement would have infinite length. Let's look at some examples of usage of universal quantifiers. So again, the positive integers. You will have these kind of examples on the homework. So that's why I want to exemplify, take a few. So for all x, p of x implies dx. Let's p of x be x is prime and d of x is odd. Is it true for all positive integers that whenever an integer is prime, then it must be odd? Well, it is almost true, but not. There is one integer that is positive and violates this. It's 2. The smallest prime is not odd. All the other primes are odd, but the smallest one is 2 itself, and it's not odd, and it violates this implication. This part is true, this part is false. Therefore, that's all you need. This is the counterexample. Let's say that, let's modify this. For all positive integers, is it the case that if an integer is prime, then it's either odd or it's a 2? And that is true, because this was indeed the only counterexample, right? For all the other prime numbers, they are odd, and therefore they would satisfy this part of this disjunction. So this part will always be true. What about for all x? If x is negative, then it's a prime. Strange, no? But look at the domain. It's positive integers. Is it true that for all x's in this domain, the statement, if x is negative, then prime is true? And it is true, because the first part of this implication is always false. And therefore, what you're saying is a statement that says something false implies, who knows? Negative numbers are usually defined as not prime, but Yeah, so this, let's say, is false also for negative integers. Well, okay, look, it has to hold for all integers. This part is false for negative, but so what am I saying? Sorry, scarces. All I need to care is positive integers. Over positive integers, some of them are prime, so they're gonna satisfy it, but some of them are not prime, so they're gonna fail that part. However, all of them fail this part. Okay, and that's why this statement for every positive integer is true, right? Because if you look at what an implication means, is that if the first part of the implication is false, you don't care whether the consequent is false or true. The implication holds, so it's true. Okay, it's tricky, and normally you would never say this if that's what's your domain. And the only context is it's a test in a logic class. De Morgan's laws for quantified statements. So here's laws of, just like we had laws for just propositional expressions, we have laws for quantified expressions, which for quantified statements. So here's the sort of the simplest in the sense, or like one of the simpler laws, is the De Morgan law. If I say that it's not true that there exists an X which satisfies predicate P, that is the same as to say that for all X's in that domain, the predicate on X fails. Okay, so both of these say the same thing, namely that the predicate is false for all X. So this is said explicitly. The predicate does not hold for all X, right? So that's what the right-hand side says. For all X, it is the case that P of X is false. Left-hand side says the same thing, because it says it is not true that there exists an X which satisfies Px. If that's the case, that there isn't a way to satisfy Px, then that means that Px is always false, right? Indeed, if you look at the finite domain, then you can, De Morgan law over quantified statement just follows from the standard De Morgan law. So look, if I say that it's not true that there exists an X such as Px, well, it is not true. I can explicitly rewrite this expression as one with disjunction. So what I'm saying by saying that it's not true that there is some X which satisfies this is that it's the same as to say that it's not true that the first guy satisfies it, or the second, or the last, right? That's how you can read off the there exists statement if you envelop the whole domain as a sequence of the elements in the domain, all right? And now by a standard De Morgan law, contradiction of disjunction of or of a bunch of things is the same as, well, if I say that it's not true that either of these things hold, then that's the same as to say that the first thing doesn't hold, and the second doesn't hold, and the last doesn't hold, right? And now I just read it off as for all X, not Px, right? So that's again just a way to read what a universal quantifier is on a finite domain. It is this thing. The second De Morgan law is the flip of it, right? Which was, so the first law was that negation of there exists is the same as for all negated statement. And here, if I negate for all, then what have I said? I said that it is not true that some predicate holds for all elements. Well, that's the same thing to say that there exists some element on which the predicate is false. right? So the left-hand side says that it is false that Px holds for all elements, and the right-hand side says there exists an element which violates this predicate. It's clear that that these are equivalent statements. And indeed, if I envelop the domain as a sequence of all its elements, this in fact holds for not just finite but also countable domains. But doesn't matter really for us here. So you can see that this is the same kind of bunch of moves, right? Reading off for all as an explicit conjunction on all elements, then applying, because it's a negation of that conjunction, applying the standard De Morgan law to say that, well, this is the same as to say that either this fails, or this fails, or it fails somewhere. And that's the same way to say it, right? There exists an element which fails this predicate. Here's an even simpler law for quantified statements. Right? If somebody says for all x some predicate holds, then it implies that there exists an x where predicates holds, right? And likewise, if it is not true that there exists an argument that satisfies the predicate, then it's also true that this predicate is definitely not true for all, right? And by the way, you can see that this thing implies this thing in at least two ways. So one is that, look, this thing is a counterpositive of this, right? What's a counterpositive? If I say something of the form P implies Q, then I can rewrite it as not, oh, this is a typo, not Q implies not P. Oh, I'll fix it on the slide. This should be not Q implies not P. If you instantiate them, right, this thing implies that, which is the same as not this side implies not that side. That's a counterpositive, except that I put a typo here. I'll fix that on the slides on the webpage. You can also use the Morgan laws, right? So look, this not negation of there exists x such that px is the same as, well, for all x, not px. And now I can use this part, because instantiated with the statement that says not px, right? Because for all, if some statement is true for all x, namely not px, then it's true for some. That's what the statement says, right? Applied to this predicate, not px. And now I can use the De Morgan, because there exists x such that px fails is the same as to say that px, it is not true that px is satisfied everywhere. Okay. Some more examples of quantified statements. Here are the common, sort of commonly occurring type of statements that occur in nature, right? So these are the natural things that people say, for example, arguing security of something, or arguing some anything really, that some algorithm works, or some mathematical formula is true, right? Or theorem is true. So somebody could say, well, there exists an x which makes the following true. In other words, it makes both p and x, it satisfies both p and x, p of x predicate and q of x predicate, right? So these are two different conditions on x, and this statement says that both conditions are met. A very natural thing. Look at this one. Somebody says for all x, it is the case that whenever p of x holds, then q of x holds. What is they saying? Well, what they're saying is that for all elements in the domain, it holds that whenever this condition is satisfied, then this condition must be satisfied too. Okay. it's so common that actually it has a sort of a different syntax in which you can state it. This is known as quantified statement. So it's typo, it should not qualified, quantified of a restricted domain. I can rewrite it like this: for all x which satisfy the predicate p, it is true that q of x. Because this statement is read like this: this predicate q of x holds for all x which satisfies predicate p of x, implicitly in the domain, whatever it was. This is exactly what this says, right? For all x for which that satisfies this, it also the q of x must be a consequence, right? These are the same statements, and this is a shortened form. This is how common these kind of statements are. But consider this one, okay? How about this one, but with a existential quantifier? So how about somebody who says there exists an x such that predicate p of x implies predicate q of x? Well, remember, if you disregard this part, your sort of a knee-jerk reaction will be to read it off this way. But it is not. It is not equivalent. Here somebody says that there exists an x which satisfies some formula. Well, this formula implication we know is equivalent to following this junction. Either the hypothesis is false or the consequence must hold. So what the statement really says is that somebody says that there exists an element which satisfies either this predicate, in other words, for which p of x is false, or satisfies this predicate, so q of x is true. That's what really this says. And basically, this form is like an honest form. If somebody, this could occur in nature. This could occur, somebody might have say, like, look, there's two types of conditions under which this code will, whatever, give you good results. Either this or that. Okay, that's maybe natural. But expressing them in this way, it's equivalent, but just tricky. Okay, people don't read off this naturally. They often forget that an implication is true if this precedent is false. They forget about this case, and basically, it's a trick way to state this. Okay, let's complicate things a little further by noting that we can you can quantify variables that participate in a predicate, and it could be a second layer to this. Okay, so it could be that you define a predicate as a quantified expression on some other variable. Let's look at an example. Take a predicate on two variables, t of xy. And take an example that what t of an xy stands for is that 2x is equal to y. Okay, that y is a double of x. And there is an implicit domain is integers. Okay, for this predicate. So for example, if t of 1 and 2 is true, right? Because 2 is indeed a double of 1. But t of 1 and 3 is false. 3 is not a double of 1. Consider a predicate on y, which says that there exists an x such that t of xy. Okay, well, in other words, this is the same as to say that there exists an x such that 2x is y. That's a predicate on y. So for example, take y equal 2. And let's see if this statement is true for it. So is it true that there exists an x such that t of x2? In other words, what does this statement say? This statement says that 2 is a double of x. And this statement says that there exists an integer such that 2 it is its double. Is this statement true? Yes, there is indeed such an integer. It's a 1. It's a unique integer. But it exists, and therefore this statement is true. Consider y equals 3. Well, then this statement is not true. It's not true that there exists an x such that 3 is its double. Indeed, for all x, it is the case that 3 is not a double of x, right? So there is no integer that makes this statement true, and therefore P of 3 is false, because P of 3 says that there is such an integer. Okay, so P of 3 is a false statement. Now, that was when I instantiated y to 2 or 3. What if I make a quantified expression involving this predicate? I can state there is a y such that P of y. Again, what was P of y? That was there exists an integer such that y is a double of that integer. So P of y is a statement that says y is a double of something. Is it true that there exists a y such that y is a double of something? Yes. For example, 2. Right? Satisfies this, as we argued here. It's not the only case. This statement is also satisfied by, for example, y equals 4. It's also true that 4 is a double of something. It's a double of 2. 10 is a double of something, right? So there is every even integer is going to be a good example for this statement being true. What about this quantified expression? Right? For all y, P of y. In other words, for all y, it is the case that y is a double of something. It is not. It's false, right? Because there exists y's for which it's not true that this predicate holds. In other words, the y's are not doubles of anything. For example, 3, but actually every odd number is going to be a counterexample to this. And now there is a nested quantifier, because look, how did I define P of y? I define it this way. So I could rewrite this, there exists y such that py, as the following statement. There exists an y such that, and now I substitute what py was, and py was a quantified statement itself. So there exists a y such that there exists an x such that t of x, txy. In other words, there exists a y such that there exists an x such that y is a double of x. And boom, it's true. You know, I just envelop and bring up the same example. And this quantified statement can be enveloped as this nested quantified statement, right? For all y, there exists an x such that y is a double of x. That's false, right? The 3 is a counterexample, and so is every odd number. Okay, in nested quantified expressions, all 3 variables must be bound by some quantifier. So for example, here, look, my predicate, I just take a particular predicate that x is smaller than y. On a slide before, I had that y is a double of x, and here I have just that x is smaller than y. All right, so look at this expression. For all x, scratch. There exists an x such that for all y, x is smaller than y. The domain is 1, 2, 3. Is it true that there exists an x that all elements in this domain are greater than it? Well, first of all, x and y are both bound. So this is a proposition. is either true or false. It is a proposition and it's false. And what's the counterexample? There is, well, for every x, I have to find the counterexample. All right? To show this is true, I have to show that for every x, there exists some y which which falsifies this. But it's simple. The counterexample for every x is y equal to x. If I make y equal to x, this statement becomes x is smaller than x. That's false, always. And therefore, it's not true that for all y's, this statement is true. Therefore, this statement is wrong, this part is wrong for all x, and therefore there is no x, which makes this statement true, right? So the proposition is false. Look at the flip. I just changed the order of the quantifiers, and it becomes a very different statement. Is it true that for all y, there exists an x which is smaller than it? Again, x and y and both are bound. It's a different statement, but well, in some sense it's not, because it's false, right? So in that sense, it's equivalent, because both this is false in the case of this domain, and this is false in the case of this domain. But this is just, yeah, just because of the domain and because of the predicate. So why is this guy false? Because there exists a y that has no smaller elements, right? So this statement means that there exists an integer smaller than y. This statement, this part, from here to here. There exists an x smaller than y. And it's true for all integers greater at least 2, right? Because 1 is smaller, but it's not true for 1, right? So there is one counterexample only for this. Make y equal 1, and this will not be true, because there is no positive integer smaller than 1. If I skip one of the quantifiers, okay, so if I have an expression like this, it is not a proposition, because y is still a free variable here, so it cannot be fully evaluated. It is, however, a predicate on y. So for particular values of y, this will get a truth value, and I can evaluate it, right? But it's not a proposition yet. It can be read and interpreted as a predicate. So anybody, if you just wrote this, I would interpret it, oh, you stated the predicate on y. Okay. Let's come back to this example of nested quantifier example. So we have this statement that y is a double of x, and the statement p, which says that p of y meant that y is a double of something, right? There exists an x such that when I double it, I get y. Okay, so in other words, the predicate p of y means that y is twice something, and that is the same as to say that y is even, right? If you think of what this means over integers, you will conclude that that's the equivalent thing to say that it's an even number. And using this predicate, I can evaluate these nested quantifiers, because I can be, okay, here somebody says there exists a y such that there exists an x such that the x. So I read off this part as this predicate. I think about it, and I understand that basically the inside here means that y is even. That's what this stands for, because I rewrite it this way, and I think of this separately. And so when somebody says that exists y that make for this, well, this is the same as to say that there exists y which is even, and that's of course true. Or if somebody says for all y's this holds, right? That is obviously false, because it's gonna, any odd number is gonna be counterexample. But these are not only nested quantified expressions that are possible here, right? For example, what if you do this? If you, instead of there exists y, there exists x, for all y there exists x, you do there exists x for all, there exists a y such that for all x, or for all y, for all x. How do I deal with these? Well, the same way. What do I have in common? This thing. For all x, g of xy. Let's define it as something. Let's define a predicate on y that says for all x, g of xy. What does this thing say? It says that, what is t of xy? That's y is 2x. So that's what it says. For all x, y is at 2x. And this nested expression can be rewritten this way. And so can this be rewritten that way, right? So let's think what this says. And it says basically some absurd thing, right? Because it says that this predicate says about y, y is a double of everything. Over integers, that's impossible. Y can be a double of at most one thing. So this y, that y is a double of all integers, is patently false on all integers. Well, that makes evaluating this really easy. They're all false, right? Okay. What about if you switch the order of these quantifiers? Because you see, we have all of them had some quantifier involving y first, and some quantifier involving x second. What if we switch that order? So here is the monstrous slide on this. Okay, this part is the same as before. Here's the new part. So consider expressions that look like this. They all involve t of xy, and they all start with some quantifier on x, followed by some quantifier on y. Okay, so let's basically apply the same procedure. So when somebody says there exists an x such that this thing, let's just focus on this thing. Let's call it s of x. It's a predicate on x, right? Why? Because basically within here, x is not instantiated. It is instantiated here, but if I just look at this fragment, it is not. That's a predicate on x. It's a predicate that reads off this. There exists y such that t of xy. What does it mean? T of xy means that 2x is y. So there exists y such that it is equal to 2x. X is a half of some other integer. Well, it's always true, right? There always is an integer that is equal to 2x. So these evaluations are simple. S of x is true everywhere. So there exists an x such that s of x is true. It's true. For all x, s of x is true. It's also true. Yes, indeed. S of x means that x can be doubled, right? There exists a y which is a double of x. Yeah. So all these statements are true. Now look at this one. What is nested in here is the statement for all y, t of xy. Let's look at that statement and call it r of x. It's a predicate on x. The predicate says, for all y, double of x is equal to y. In other words, x is a half of every integer. If you double x, you get an integer, and that's true for all integers. You know, you get a y, it's true for all y. Well, that's patently false. It cannot be that x is a half of every integer, right? So this predicate is false for all x. And so these statements are also easy to evaluate. They're both false, right? Indeed, there's relations between these things. So the relations are that if you have a sequence of same type of quantifiers, there exists a y such that there exists an x which makes this true. I can reorder the order of these quantifiers. I can express it this way, right? And I had a different argument for why that was true, but the fact that it's true or not did not change. Okay? In fact, this shows you that if you have a statement like this, and now you have to think something, okay, maybe you can reorder these and think instead of this statement. And that will like be a triviality, actually. X is half of some integer, and therefore you can immediately say it's true, right? Whereas this part was not triviality. This part said that y is a double of something. So the y is a double, so y is or even. Nevertheless, these quantified expressions were the same and can be, they're always, regardless of what t is, this black dot, these two expressions are equivalent. Why? If basically, what is the statement? It says that there is some value y and x which makes this true. Well, this is the same. There is some value of x and y such that this is true. That's the same. There is some assignment to these arguments which makes this expression true. Likewise, the orange expressions are the same. All right, so if somebody says that for all y, for all x, something is true, that means that for all assignments to x and y, this predicate holds. And this thing expresses the same thing. For all assignments of x and y, this predicate is true. So these orders can be flipped. These cannot. And so, for example, here, look at the second row. This thing happened to be true, false, but this thing happened to be true. All right. Okay. That was it. All right. So this is a different format lecture. You have no chance to ask questions on Zoom. You know, ask them on Piazza, ask them in discussions. Thank you so much for listening. Till Tuesday.